Bismillahirrahmanirrahim. So from last two discussions, we come to know that the solutions to planar dynamical systems of this form x prime of t to be equal to ax depend on the eigenvalues. So they depend on the eigenvalues. So we will be considering cases on eigenvalues, and we will be studying the behavior of such dynamical systems. So let's first consider, let's say it's a case one or example or one or whatever you call it. Let me consider one particular system where x prime is equal to ax, where a is given by lambda 1 0 0 and then lambda 2, with I will consider lambda 1 less than 0 and lambda 2 greater than 0. So this system is nothing but x prime is lambda 1 x and y prime is lambda 2 y. So this is my system, and here lambda 1 is less than 0 and lambda 2 is greater than 0. I want to study what is happening to this system, how the behavior of this system looks like when lambda, one of the lambda is positive and other is a negative. So in this case lambda 1 is assumed to be negative and lambda 2 is assumed to be positive. So let's find out the eigenvectors first. So for lambda to be lambda 1, let's find what is eigenvector. We know that for such thing, we for finding out the eigenvector, we all we do is we solve a minus lambda I and operating on to x to be 0. So let me do this here. So my a is lambda 1 0 0 lambda 2, and my lambda, this for this case is lambda 1, and this is 1 0 0 1, and all of this thing is operating on to a vector x to be 0 0. And then you can see that this is going to be okay. So this is 0 0 0 lambda 2 minus lambda 1 times x with y to be equal to 0 0, and this implies that lambda 2 minus lambda 1 times y is 0. But we know that lambda 2 and lambda 1 are not equal, as one of them is positive and other is negative. So that implies y is 0. When y is 0, but x can be anything. So like x can be anything. Let me say t. So the eigenvector should be x comma y, which is t comma 0, or you can snatch out t and this is 1 0. So this is really eigenvector 1 comma 0 is going to be my eigenvector. So for lambda 1 less than 0, my eigenvector is v1, which is 1 comma 0, and it is not hard to show, which you can calculate by yourself, that lambda 2 when is positive, for lambda 2 your v2 is going to be 0 1. And what do we have from here? So for our system, one solution is going to be x1 of t, which is equal to e to the lambda 1 times t 1 0, and x2 of t is going to be e to the lambda 2 times t, and this is 0 1. And in this way, the general solution would look like x of t to be alpha times e to the x1, which is e to the lambda 1 times t times 1 0, plus beta times e to the lambda 2 t times 0 1. So this is really going to be the general solution to my considered system, where lambda 1 is less than 0 and lambda 2 is greater than 0. So we have this thing over here now. We have the solution, general solution, which is x of t to be alpha times e to the lambda 1 t 1 0, plus beta times e to the lambda 2 t times 0 1. Now let's talk about this first solution where lambda 1 is less than 0. You know that this lambda 1, for this lambda 1, this x1 is uh, this quantity e to the lambda 1 t 0. This is going to be x1, this one over here. This is nothing but this is something which lies on x-axis as t varies, because as t will be vary, x will be some value and y 0. So this lies on x-axis, and as t goes to infinity, we know that lambda 1 is less than 0. So this quantity must converge to 0. And this way, this x1 of t, which is this over here, should go to 0, 0, which is origin. So because this x1 of t uh, goes to 0, 0 along this x-axis, therefore in this case people call this x-axis as the stable axis, or you can call it a stable line, or people also call it this is x-axis. And for this example, x-axis is stable manifold, is a stable manifold. Why this x-axis is stable manifold? Because along with this x-axis, solution tend towards 0. Okay, 0, 0 origin. On the other hand, you can see that on the other end you can see that is lambda 2 is greater than 0, and our solution, this is x2 of t, which is roughly like it's 0 beta times e to the lambda t. Okay, so we know that as t will go to infinity, this quantity being lambda positive will diverge towards plus infinity, provided this beta is positive. If it's negative, then it will move to negative infinity. So this will be moving away from 0, 0, move away from 0, 0. This x of x2 of t will move away from origin. So people call this axis, this y-axis, as the unstable axis. For this example, it is unstable axis, or you can call it, it is y-axis is unstable axis, or you can call it unstable line, or you can call it unstable manifold. So why? Because along with x-axis your trajectories will, along with y-axis your trajectories will be moving away from 0, 0. Our 0, 0 was fixed point. We can see that this 0, 0 is a fixed point. No one can you can see that because x prime was x, and we know that 0, 0 is its equilibrium solution. So along x-axis the trajectories are moving towards this, and along y-axis they are moving away from 0, 0. So what is overall behavior? Let's categorize it. Let's draw this behavior overall. So let me say, okay, so this is over here, this is my y, this is x, this is x prime, this is y prime. This point over here is 0, 0 origin. Now if any trajectory is moving from here, then we know that x-axis is our stable line, so it will be moving on towards 0, 0. But we know that y-axis is the axis which is unstable, so it will not allow it to go towards 0, 0, but it will snatch it towards it this way. If any trajectory is going from here, then it will be moving this way along with unstable. This had to be this. Okay, so this way like this. If any trajectory, so this will be directed towards this. Any trajectory is moving from here towards 0, 0, then it will be reflected towards this y-axis. Similarly, from here it's moving towards 0, 0 along x-axis, but then with y-axis it goes like this. Okay, so any other trajectories will be behaving something like this. and people call this behavior as saddle. So the equilibrium point in this case will be saddle. Equilibrium point, which is 0 0, is saddle, and it is indeed unstable. Why unstable? Because the nearby trajectories don't remain close to 0 0. You can see previously the definition in the previous videos what is unstable point. So it is unstable. Saddle is an unstable. So for x1 of t, one more thing that I want to mention, x1 of t was equal to lambda 1 times e to the lambda 1 t times 1 0, and x2 to lambda 2 times e to the lambda 2 t 0 1. And as t was going to infinity, we were moving towards 0 0 along this stable line and away along with this unstable line. But if you allow your t goes to minus infinity, then this stable line, the trajectories will be moving away from 0 0 along this stable line, and the trajectories will be moving towards 0 0 along this unstable line, because this, if you are allowing t to go to negative infinity, this behavior will be opposite, because lambda 1 is negative, negative times negative positive. So this will be snatching away your trajectory from 0 0, and this will be moving your trajectories towards 0 0. I hope it makes a bit sense. So let me make this more clear. For the system x prime to be ax, with a being lambda 1 0 0 lambda 2, with lambda 1 less than 0 and lambda 2 greater than 0, the the 0 0 is equilibrium point, which is saddle and is also unstable. Okay, so from now onwards, in general, you will be also looking at this behavior, that if lambda 1 is less than 0, one of the eigenvalue is less than 0 and other is greater than 0, then the equilibrium solution will be showing you the behavior like saddle. Thank you.